Hi everyone! In this video we are going to learn about polarimetry. But first we need to talk about compounds that are optically active. So one interesting thing with certain compounds is they can rotate light. So for instance, some compounds can rotate light 20 degrees or more depending. So let's draw a couple of compounds here. So I'm going to draw a carbon bonded to bromine, hydrogen, fluorine, and chlorine. All right. Now let's assign R or S to this compound. So remember, the first thing we have to do is prioritize the substituents that are attached. So what would come first? Bromine, chlorine, fluorine, or hydrogen? Bromine would come first because it is the heaviest atom that's attached to carbon. What would come next? Chlorine, fluorine, or hydrogen? Chlorine. All right, and then what comes next? Fluorine or hydrogen? Fluorine. All right. So we have our priorities there, and our lowest priority atom, hydrogen, is in the back, so that's good. So let's draw a circle from 1 to 2 to 3. And if we imagine that it's a steering wheel, we're rotating our steering wheel to the right or in a clockwise direction. So is that R or S? R. Okay, so this particular molecule has an R conformation, and it can rotate light. Now, let's look at its mirror image. So the mirror image of our molecule also has a stereocenter. It's also chiral. It has 4 different bonds to that carbon. So let's assign R or S to this mirror image. So the priorities will stay the same as our original molecule. And then we're going to draw our circle from 1 to 2 to 3. And if we imagine a steering wheel, it's going towards the left in a counterclockwise direction. So is this R or S? S. Okay, so previously we said that if mirror images are non-superimposable on each other, they are chiral. And another term for mirror images that are non-superimposable is enantiomers. So we're going to start using that word to describe these mirror images that are non-superimposable on each other. Okay, so these enantiomers are chiral, and they can each rotate light. So they are both optically active on their own. So if we were to just isolate the R molecule, it would rotate light in one direction, and the S molecule would rotate light in another direction. So Let's see. These molecules are chiral and optically active. Now, how do we determine how much of a rotation these molecules can perform on light? Well, we use something called a polarimeter. So this is an instrument that we use to measure the rotation of light for a particular sample. You can also measure the rotation of a mixture as well, although we'll talk about in a second what happens if you have a 50-50 mixture, so exactly equal amounts of R and S, or if you have more of one enantiomer than another. So let's talk about how this polarimeter works. And this is a simplified diagram. But basically you start with a light source, and most often we use a sodium lamp. And the sodium lamp emits light at a fixed wavelength of 589 nanometers, which is also called the D line of sodium. So that light passes through a lens, and then it passes through a polarizing filter. So initially you have all different directions of light. It's just rotating in all directions. But when you pass it through a polarizer, then you end up with just one direction of light. Now that one, what we call polarization plane, passes through a sample in this tube here. And if that sample is optically active, it's going to rotate that light in a certain direction at a certain number of degrees. So here at the end of the tube, you can see that the sample did rotate the light slightly. So instead of pointing up and down, now it's more diagonal. And then we can measure the angle difference here between our original polarization plane and then the resulting plane. So that might be something like 5 degrees, maybe 10 degrees, something like that. And then finally, that will pass through a lens, and we will measure the degree of rotation. All right. Now, again, chiral molecules will rotate light. So if we look at our molecules that we drew on the last page, let's say hypothetically that the molecule on the left rotates light 20 degrees. Now, it can rotate light in either a positive direction or a negative direction. So let's say it rotates light in a positive direction. Its mirror image, its enantiomer, will rotate light in the opposite direction, but it will have the same magnitude of rotation. So the molecule on the left rotates light in a positive 20 degrees, and its enantiomer will rotate light negative 20 degrees. And this is just a hypothetical situation. These might not be accurate numbers. So the molecule on the left, because it's rotating light in a positive direction, that's referred to as dextrorotatory. And if something rotates light in a negative direction, that's referred to as levorotatory. Now, there is no connection between R and S and positive and negative. You might have one R molecule that is dextrorotatory, and then you might have a completely different molecule that's also R, and it can be levorotatory. So R and S has nothing really to do with whether a molecule rotates light positively or negatively. Now, let's say we have a 50-50 mixture of both of these enantiomers. So we have equal amounts. Then what would happen? Any guesses? Would we see any rotation of light, or would we still see some rotation of light? Well, if we have an exact 50-50 mixture of our positive 20 degrees and negative 20 degrees, then they're just going to cancel each other out. And we would see no rotation of light. Now, if you had just the R conformation, then you would see that positive 20 degree rotation. And if you just had the S conformation, then you would see a negative 20 degree rotation. But if you have a mixture that's not 50-50, so let's say it's 70-30, then you have an excess of one of the enantiomers, and you're going to see a certain rotation of light. But we'll talk about that next. So let's talk about something called specific rotation. So actually, we're going to write here specific rotation, because the specific rotation of a compound is defined as the observed rotation under specific conditions. All right. So this is given the symbol alpha in brackets. And then on the upper right-hand corner, we can indicate the temperature of the sample, which will be in degrees Celsius. So typically it will be 20 degrees Celsius. And then we can also indicate on the lower left, or lower right, excuse me, the type of lamp that we used. So this will be our sodium lamp, the D line. So that was 589 nanometers. Now this specific rotation depends on a few different factors. So this is equal to the observed rotation. So maybe that's positive 20 degrees. And then we'll divide that by the concentration of the sample. And that will be in grams per milliliter. Oops. And then we'll multiply that by the path length that the light travels through. And that will be in decimeters, which we don't really use very often. In fact, this is one of the few cases where we do use decimeters. Now, remember that 1 decimeter is equal to 10 centimeters. So that's just a quick note there. All right, so let's plug in some symbols for each of these different factors for specific rotation. So observed rotation is given the symbol alpha. And then concentration is given the symbol C, and path length is given the symbol L. So this might look pretty similar to Beer's law, if you remember that from general chemistry. And it is pretty similar. We're still dealing with a measurement of light. All right, so again, if you have a 50-50 mixture of R and S enantiomers, then their different rotations are going to completely cancel each other out, and we won't see an overall rotation of light. So our specific rotation would just be 0 degrees. But if we have an unequal mixture, then one enantiomer will be in excess and will rotate the light. So let's just write that down real quick. One enantiomer, or mirror image, will be in excess and rotate the light. So let's figure out how we can calculate the amount of excess enantiomer we have, because typically we don't know how much is in a sample. We're trying to kind of judge, is this all R? Is it all S? So let's see how we can figure out how much excess enantiomer we have. So this calculation is for something called Enantiomeric Excess, which we abbreviate as EE%. So EE%, or enantiomeric excess, is calculated by taking the specific rotation that's observed. Oops, that looks like ABS. That should be OBS for observed for the mixture. And then we're going to divide that by the specific rotation that's observed for the pure substance. So that's going to be either just R or just S. It depends on what you're comparing it to. And then we'll multiply this by 100. So let's do a practice problem for this type of calculation. Let's say a mixture of enantiomers, so mirror images, has an observed specific rotation equal to positive 5 degrees. So it's dextrorotatory. The pure enantiomer, so let's say that's R. I don't know which one it is, but let's say it's R. Has an observed specific rotation, oops, D20, equal to positive 10 degrees. What is the enantiomeric excess? Okay, so we want to figure out how much of our mixture is just R and how much of the mixture is S. Okay, so a fraction of our mixture will be a 50-50 mixture of R and S, and then we'll have excess R, for instance. All right, so let's figure this out. Let's plug in our values for EE%. So again, we have the observed rotation for the mixture. So we set up above that that was 5 degrees. And then we're going to divide that by the observed rotation for the pure substance. So that was 10 degrees. So that means that we have, oops, we also have to multiply it by 100, I forgot. So that means we have a 50% excess of R. Okay, so now let's figure out how much of our total sample is R versus S. All right, so we said we have 50% excess R. So that means that the other 50% of our mixture, the other 50% of our sample is a mixture, right? So the total minus the excess R will equal how much mixture we have, which is R and S. So let's say our total is 100%. We'll subtract 50% for the excess, and that gives us, okay, 50% of our sample is a mixture of R and S. All right, so now the amount of R will equal the amount of excess plus half of the mixture. Because remember, half of the mixture is R, half of the mixture is S. And then we have our excess R as well. So this will equal 50% plus half of our mixture, which was also 50%. So that's 50 plus 25%. So 75% of the sample is R. So now let's figure out the amount of S. So the amount of S will be the mixture, let's see. So the amount of S will just be half of the mixture, which is half of 50, which is 25%. Okay. So this is just an example of how we can figure out how much of each enantiomer we have in a mixture. So again, going back, we would measure the rotation for the mixture and then the rotation of the pure enantiomer that we're interested in. So in this case, we just picked R arbitrarily. But in an actual experiment, we would be picking based on other factors. And then we just used this percent EE to figure out how much excess R we had. And then we just used some simple addition and subtraction to figure out how much of our sample was composed of R and how much was S. And sometimes it can get a little confusing because if you're not sure which one is which or you get them mixed up, that can happen. But I just wanted to kind of show you how scientists use polarimetry with what are called racemic mixtures or with mixtures that have excess R or excess S. All right, so that's the end of this week's material for Chapter 5. Next week, we'll cover the other half of Chapter 5, and we'll start diving a little bit deeper into different types of isomers. We'll talk about enantiomers some more. We'll talk about something called diastereomers. So we'll get to cover all of that next week. So I will see you then.